Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we will derive the equation for discharge, work done and power required to drive a single acting reciprocating pump. So in our last lecture, we have seen the working principle of reciprocating pump. Now we will derive this equation for that. So this is the schematic diagram of the reciprocating pump, which I have taken from the textbook. So before going to derive this equation, let me just give a brief idea about it, how it is working. So actually this is the sump level. So in the sump level, or you can say this is a reservoir also. We can call it this is a sump level, or we can call it as a reservoir of liquid or water. So this is the schematic view of the pump. Okay, so this is the pump like piston, and the piston is connected with a piston rod, and the piston rod is connected to this connecting rod, then a crank. That means the piston is connected to the crank with the help of piston rod and the connecting rod. Okay, and this piston is placed inside a cylinder, inside a closed cylinder it is kept. So suppose before this diagram, let's suppose this is the piston is there, and this is the cylinder, and the piston is present at this point. Okay, so the piston is present at this end of this cylinder, and like this this is the piston rod, and the piston rod is also connected to this one connecting rod, and the connecting rod is connected to the crank. Okay, so this is the crank is there. Let's suppose this crank is at this point, 0 point, and this is A point. Okay, now and the crank will be connected to a motor. The crank will be connected to a motor to drive. Okay, so when the motor will be started, the crank will start. The crank starts rotating. So when the motor started here, you can write this is motor. Now when the crank is started, so that will started rotating here. So that means from this A point it will start rotating. When it will start rotating, this connecting rod also will move. Along with the connecting rod is connected to the piston rod, so piston rod will start moving. That means the piston started moving from this point to, like, from suppose this is our left side. From left side to it will move to the right side. Okay, and as we can move like this from suppose this is 0 degree angle is there, and slowly the angles also you can see this is angle of theta. Okay, so this started increasing. Now suppose here it is 90 degree, we can give a point B, then again it's moved up to this much distance, again some distance. So that means here also our revolution will be there, like here also we are having the movement. That means the crank is moving, this crank is moving from A to B, then B to C, and this is our suppose 180 degree. That means the crank moved from 0 degree to 180 degree. Then again also it will continuously, it will moved like here 180 to 360, like means one half revolution completed up to here, it came here, then again it down. This is C point, this is T point, and this will be our 270 degree, this is our 360 degree or 0 degree. Now when the crank moved from here to like A point to B point, B point to C point, then we can say this is the suction stroke done. From that means the piston moved from left to total right here up to here. So now it is moved up to here, this point. Okay, so that this length, actually the movement of this crank, okay, that is L, which you can write this is 2R, and that is length of the stroke. Actually that is length of the stroke. Now when it will complete one revolution, in the sense A to B, B to C, again C to D, again D to A. So when it will complete one revolution, then we can say like this, one complete revolution discharge will come. That means this piston when came to here, again this is half revolution completed. Then when it will go again from here to, again it will come down. That means this is suppose forward, and this will backward. Okay, reverse direction. So now from right to left, the piston will start moving from here to here. Now this is from right to left direction movement will be there. So in that time, what will happen? See, when the piston will move from here to here, by the in meantime, the water will be lifted from the sump level, from the reservoir, and it will come here in the cylinder. It will fill up water. Okay. After that, when it will be goes back, like the piston will goes back, then it will be move out from here. So meanwhile, it will be closed. This valve will be closed. This valve will be opened due to the pressure difference. So all the details I have explained in the working principle. Just I'll give a just brief idea. So the water will be goes out. Now see, from this sump level to this delivery point, okay, the total distance or the total height, here it is the suction head, HS. So from this point, if you consider, this is your suction head and this is your delivery head. That's why it is HD. And this is the theta, which is the angle of this, and the stroke length. So to calculate the discharge, okay, that means how much amount of or how much volume of water is discharged by the pump. So how we can calculate? So let me give a small example for this, then we'll go for the derivations. Suppose in one revolution, let's suppose one revolution, okay, in one revolution we have suppose 20 meter cube per second of water delivered. That means this much discharged done, this much 20 meter cube per second of water or liquid, any kind of liquid is delivered. That means the water can be delivered 20 meter cube per second of one revolution. Okay, but one revolution, that means total complete here. Now if I'll ask that 1 second, how many revolutions are done, because we are going to calculate with respect to time, okay, with respect to per second also you can consider. Now if suppose, if I'll consider in 1 second, in 1 second, how many revolutions are done? In 1 second, suppose 5 revolutions are done. Suppose 5 revolutions done. Then what I can say, in 1 second, 5 revolutions. So one revolution, this much water delivered. So 1 second, this how much water delivered? So you can write this 5 revolution with respect to what is the quantity, what is the volume of water? That is 20. That means in 1 second we can write 100 meter cube of water is delivered. Okay, so this much volume of or this much discharge of water happened from this reciprocating pump with respect to 1 second. Okay, now so we need to calculate the discharge. Now this is with respect to, suppose when you calculate the discharge, that means we need, for to calculate the discharge, we need discharge in one revolution. This is what we calculated, discharge. We need to calculate discharge in one revolution. Okay, discharge in one revolution into number of revolution in 1 second or per second. So here number of revolution, how much? 5 I have taken. Just have taken one example in 1 second or per second. So here also we can write into the number of revolution you can write per second. So these things we need to calculate, or these things will give us the value of discharge, okay, of the pump per second. Discharge per second, let me write per second. Now before that, before going to derive this, let's consider some few terminology which are involved in this concept. So these the things we need to consider. First one is diameter. Okay, D is the diameter of the cylinder. Where the cylinder is there, this is the cylinder. So diameter, we need to consider D is the dia of cylinder. So these things I won't write, just I'll tell you. You can note it down or you can remember it. So D is the diameter of the cylinder. Next, A is the cross-sectional area of the cylinder or piston. Now here D is diameter of the cylinder, or we can also consider for the piston also. Okay, actually both are not exactly same value. If the mm of gap will be there between, okay, this cylinder and the piston, so that clearance will be very less. So that's why we used to consider the diameter of the cylinder and piston both are nearly equal. Okay, so sometimes it will be given, let consider, in the question will be given, let consider the diameter of the cylinder and piston both are same, let consider the value of diameter is 20 mm or 30 mm, something will be given like that. But the clearance between this piston and cylinder will be very minimal. And here also we can write this is the area of same thing, cylinder or piston we can consider. So area, how we can calculate here, though you can see it is a circular one, so we can calculate this is pi by 4 into d square. Okay, and the next one is radius r, the radius of the crank. Here if you see the crank which is given, okay, like which is connected here, so radius of the crank is r. So this is r is the radius of crank. Okay, now the next terminology we need to see that how it is moving when it is rotating, so how much speed it is. So that is nothing but n we can consider, that is speed of the crank, speed of crank, or we can say the rpm, how it is rotating, that when you can say rpm, and this rpm is need to consider the revolution per minute. Okay, revolution per minute we need to consider. And one more is there, L, what you can see, that is L equal to, that is the length of the stroke. This is length of stroke, so that can be calculated by 2 into r. Okay, because this is one r and this is another one, so the total is, we need to consider 2 into r. This is length of the stroke. Now along with that also we can consider this is HS and HD. So HSHD, I already told you that this is the height from the axis of the cylinder, like from the center point of the cylinder to the surface of the reservoir or sump level, that is HS, and HD equal to from the center point of these two to the delivery point. Okay, so HD delivery height we can write, delivery height from the center, and this is our HS equal to, we can write that is height of the cylinder from the water surface, height of this one, height of axis of the cylinder from the water surface, height of axis of cylinder. Okay, so these are the terminologies are required to derive our discharge, work done, and power of reciprocating pump. Now let's start here. So now as I told you that discharge I can calculate by this formula. So let me write. So number of revolution per second. So here two things we need to calculate before going to calculate these things, like discharge in one revolution and number of revolution per second. So let's calculate. So discharge in one revolution, discharge of water in one revolution, discharge, this one, first one, discharge in one revolution, or this one actually we can also consider the volume of water delivered, the volume of water delivered in one revolution. So that also we can, this last means this or this we can write, volume of water. So how much we can write, this is volume equal to, we can write area into the length of the stroke. Okay, so that is area into length of the stroke we can write. This is first one. Second thing is what, number of revolution per second. So number of revolution per second also we can write, this is number of revolution per second. Per second how much we can write, this is nothing but n, number of revolution, that how much it is rotating, what is the speed of that with respect to per second, n by 60 you can write. So now from here, from these two equation, this is the value and this is the value, so we can write Q equal to, here as I told you, discharge per second, discharge in one revolution, that is A into L. Area also you can write pi by 4 d square also you can write. L equal to 2 pi also you can put it the value, and this is n by 60. So this is our first equation what we got for the discharge. Okay, I hope you understand how we have derived this. Now Before going to calculate the work done, okay, before going to calculate the work done, let's find out the weight of the water. The weight of water, the weight of water delivered. Okay, let's find out this. How you can calculate this? The weight of water can be delivered per second. Again, also here also let me consider per second. So this is weight equal to, we know that we can write weight equal to W equal to M into G. And this M value I can identify from the density. This is density equal to mass by volume. So we can write M equal to rho into volume. So these things we can write. Now here's the same thing, I put it here on behalf of M. Okay, per second, so mg per second, suppose. Now here I'll put the value of rho into V into G with respect to second time. So this volume per second, okay, if you see, volume per second is nothing but volume of water here per second. Okay, that is nothing but discharge. So I can put the value of here rho G Q. This is nothing but weight of water delivered. So discharge per second, so that one we can write here. So here, from here we can write W equal to, this is rho into G. What is the value of Q? That is ALN by 60. So this is our weight of water will be delivered with respect, like per second. Okay, this is about the weight of water. Because why I have calculated this weight of water? Because this will be helpful for to calculate in the work done case. So work done, actually work done per second, again we'll write the next one. We'll start from here. Work done per second. Okay, so work done per second, what we can write? So this, we know that force into distance actually, but here we can write the weight of water, how much it is lifted. Okay, that is nothing but the force acted. So the weight of water, the weight of water lifted, weight of water lifted per second, again lifted per second into the distance. How much distance? That means total height of water lifted, total height. So total height, how much? If you see the total height which is lifted from the sump level to the delivery point, how much is there? HS and HD. So that we can write in terms of, so the work done per second is nothing but, I can write W into here HS plus HD, because that is the, here HS plus HD is nothing but total height through the pump, like from which the water will be delivered, like from the sump level to the delivery point. So that is HD, HS plus SD. Now we can put the value of W here, and we can write this is rho G ALN, this is rho G ALN by 60 into here HS plus HD. This is our work done per second. This one we can write work done per second. Okay, now once you calculate the work done value, the next is very simple to calculate the power. So power is nothing but, power required. What is power required to drive the pump? So power equal to, we can write this is work done per second, by 1000. Okay, so actually this work done per second, work done if you write, that is in joule. Just me tell you the unit, and joule per second. So joule per second, we can write this is 1 watt. Okay, and if you want 1 watt, you want to convert into kilowatt, just you divide 1000, that is kilowatt. So similarly here also we can write power equal to work done per second by 1000. So here I can write P equal to, just I'll write P equal to rho G ALN into HS plus HD divided by 60 is there, 60 along with 1000. Why this 1000? To make it in kilowatt. So this is our power required to drive the pump. Okay, this is the power required and this is the work done per second, and this is the discharge. Okay, this is the discharge value. So these three things, I hope you understand how to calculate or how to derive this. So the same thing we are going to use the problem in the future lectures. I hope you understand. If you are having any doubt and query regarding this, you can give a comment on the comment box. Thank you all.